Hey everyone, welcome to day 8 of our derivatives and integrals challenge. So today we're going to differentiate this one with implicit differentiation and then another integration by parts. Okay. So again, you guys should try these first, pause it, and then see if we have the same answer. For the derivative, we're going to use implicit, and so on the left-hand side, again, this is always with respect to x. So the left-hand side, the derivative of ln is always 1 over. So 1 over xy times the derivative of the stuff inside the brackets. That's the product rule. So that'll be 1 times y plus x times dy dx, like so. And then on the right-hand side, again, differentiating with respect to x always, that's 2x plus 2y times dy dx, right? And now we're going to have to isolate the dy dx. That's what we're after all. And so let's expand and isolate. So on the left-hand side, y times 1 over xy, the y's are going to cancel out. So that's 1 over x, and then plus 1 over xy times x dy dx. The x's are going to cancel out. So that's 1 over y dy dx. And then here we're going to have, again, 2x plus 2y times dy dx. Now let's isolate the dy dx, moving it all to one side. So let's move, I'll say move this over here. And let's get all the not dy dx terms onto the right-hand side. And so that'll mean, that'll mean 1 over y. 1 over y, I'll do one step at a time, dx, minus 2y dy dx. That'll be 2x minus 1 over x. Now let's factor the dy dx from both terms to isolate it. So we have dy dx, it's a y, times 1 over y minus 2y is equal to, we could multiply this by x over x to get a common denominator, with the whole right-hand side onto one common denominator. So that'll be 2x squared minus 1 all over x. And then we're going to divide through by this bracket, right? So we will, and even this, we could multiply this by y over y to get it all onto a common denominator with just one term. And so maybe that's a wiser move. Let's divide both sides by 1 minus, that'll be 2y squared all over y. Same thing here, divide by 1 minus 2y squared all over y. And now we have a fraction divided by fraction, right? You guys know how to deal with that. Flip and multiply the numerator by the flip reciprocal version of the denominator. You guys get it. These cancel out, and so we end up with, let's see where I have room here, dy dx, our derivative function, after all. Again, flip and multiply, so we're going to have y times 2x squared minus 1 all over x times 1 minus 2y squared. And here we are. There's our final answer. That takes care of the derivative portion. Did I just spell differentiate? Let's fix that. Not much to say about that one. All right, here we're going to use integration by parts. I'll remind you of the relevant formula. So the integral of u dv can be equivalently written as uv minus the integral of v du. And so we must make appropriate choices for the u and the dv collectively, respectively, rather. So this one's going to be a bit different than the last few, in the sense that we want to make our choices for u and dv again, but we might look at a tiny bit different. Now, x, we can kind of go either way. If we differentiate x, it becomes 1. If we integrate x, it becomes 1/2 x squared. Neither of those are super terrible to deal with, right? But the other part, pretend that was there all along. The other part, the ln of x dx, right? Or rather just the ln of x, I guess, for now. The ln of x is not as easy to differentiate as it is to integrate or to anti-differentiate, right? The derivative of ln x is just 1 over x. Super simple. The antiderivative of ln x, not so simple. Probably not anything you want to deal with, right? Just a simple analysis like that is going to lead you to make your choices super fast, right? We do not want to have to anti-differentiate ln x. We want to differentiate ln x. And so by that logic, let's make ln x our choice for u. In that case, du will simply be 1 over x dx, okay? And then we'll make dv x dx, right? The rest of the integral. And so that'll be x dx, and its antiderivative will be 1/2 x squared. Now, that's a higher exponent, but that's just a polynomial term, not super terrible to deal with. So let's apply our formula for integrating by parts. So this integral is going to be u times v, right? uv. So u times v is going to mean 1/2 x squared ln x minus the integral of v du. And you'll see how those two interact in a convenient way. Let's say 1/2, that'll be in front, right? A constant multiplied. And then x squared times 1 over x is just x, right? And that is already super convenient. We can evaluate that with just a tiny bit of cognitive effort, let's say. So our entire integral drops down to 1/2 x squared ln x minus 1/2 times the integral of x dx, you know, is simply 1/2 x squared plus c, right? Integrating constants. Let's not forget about that one. And so we can clean this up. And so we have 1/2 x squared ln x minus 1/4 x squared, let's say minus 1/2 c, right? And then maybe you want to factor out a 1/2 x squared from the first two terms. That'd be fine if you want to. No, not necessary, but maybe not a terrible idea. So we have 1/2 x squared times ln of x minus 1/2, and then minus 1/2 times some integrating constant c. And we're done. So another nice example of an integral evaluated using the integrating by parts formula. Again, if you're starting to see some patterns with your choices of u and dv respectively, a really good idea is to do a simple analysis of the two parts, no pun intended, of your integral. And if there's one that you can kind of differentiate or anti-differentiate, let that one go. Deal with the more complicated part. Ln of x, again, is much easier to differentiate than to anti-differentiate. That should kind of lead you along the way of the most efficient path forward. So, hope this helps. Please leave a comment below if you guys have any good questions for me to do. And thanks so much for watching.